Hi, so this is my presentation for the final project. And so I did different sorting algorithms and efficiencies for large arrays. And of course, my name is MJ Ruman. And so why this topic? So sorting algorithms are the essential block of computer science and engineering. Sorting data allows for easy access, efficiency, easy data management, and data compressions. It is essential that we learn different sorting algorithms to be able to advance in your career if you are working with large portions of the data. So let's say you're a computer scientist and you have an array of this data that you gather. You're going to need a way to be able to sort that data, to read it more efficiently, get it in reports, and just basically do your overall job. And so I stumbled on this topic while I was laying in bed one night scrolling Instagram, and I saw a YouTube video basically describing the different types of sorts. And so I will now pull up that YouTube video. If you give me a second. So this is the YouTube video that I saw. And so as you can see in this top left corner, it will show you what different sort it's doing. It'll show you the comparisons and how many array accesses it has. So let me go ahead and play that. And as you can see, it does a lot of comparisons very quickly. And so we can just go ahead and go through, and then we have our insertion sort. It does this, which is awesome. Just go ahead and mute this. And so you can see the insertion sort, and then we have a quick sort here. And then, so that's the quick sort. Then we have a merge sort that we learn in class. We have a heap sort. And so this is just kind of where I got that whole, project idea from, and I thought it'd be interesting to do it with massively parallel processing. And so now we're back at this slide. And so next slide, I went over 3 sorts. So the first sort is going to be a bitonic sort. So bitonic sort does O log base 2n comparisons, and so it only can be done if the data size is a power of 2. This is very important when we go and look at the actual code, because for larger arrays, you're going to have them be like 10,000, a million, 3 million. They're not going to always be powers of 2, and so you're going to need to add padding and everything. And so this bitonic sort is really good for parallel implementation because we compare elements in a predefined sequence, and the sequence of comparison doesn't depend only on data. And so I made a little graphic out to the side so you can see that our starting is our size of the array is 8. We have numbers 1, 2, 3, 4, 5, 6, 7, 8, and they're just in a different order. And so first thing we're going to do is we're going to split it basically down the middle into 4 and 4. And so the first half of it is going to be ascending, and the second half is going to be in descending order. This is very important to know. So what we're going to end up doing is comparing the first element to the fourth element. So as you can see, we don't need to switch. As you can see on our first element to the fourth element, or first to the fifth, which is 0 and 4, we compare those, and then we can see that they don't need to switch. Then we do 4 and 5. Again, don't need to switch. 7 and 2, they do need to switch. 8 and 1, they do need to switch. And so we separate it when we do the 4. Now we're going to be only looking at 2. So that 2 and that 3 is going to be flipped. As you can see, we have the 2 and the 3. 2 and the 3 is going to be flipped. We do the 4 and the 1. 4 and the 1, that's going to be flipped. We do the 6 and the 7. 6 and the 7 is going to be flipped. And the 5 and the 8 is not going to be flipped. Then we do the last one, which is the side-by-side. We say, okay, is 2 and 1 going to be flipped? It is. So we go ahead and flip. It's going to be 1, 2. 3 and 4 doesn't flip. 5 and 6 does end up flipping. And then we just have 7 and 8, which don't end up flipping again. This is what the bitonic sort is. And so the next sort I did is an odd-even sort. And the odd-even sort is a variation of a bubble sort. And so it has 2 phases. It has an odd phase and an even phase. And so the odd phase, we perform a bubble sort on odd indexed elements. And so And then on the even sort, we do it on the even indexed elements. And the complexity of this is our operations times the size of our array squared. And as you can see, we go ahead and we start from the first element. And so we say, okay, we're going to go ahead and swap all these. Now we're going to start here at the quote-unquote even phase. And so we only do 3 comparisons here. Then we go back to the odd, and it just flip-flops, flip-flops, flip-flops until we get our totally sorted array. And that's what you see here at the end. And so our next is a bucket sort. And so you basically get to choose the number of buckets you want. Then you take each element in the array from the input and multiply it by the bucket array size. So we have 4 buckets in this example, so we multiply 0.05 by 4. That gives us a 0.2. Then we're going to convert that to an integer, and that gives us the bucket index number to put it in. So 0.2, what does that mean? What is that when we cast it to an integer? That's a 0, so it goes in the 0 bucket. And we just do that for every single element in the array to get our buckets. Then we complete a sort inside of the buckets. And that is how you do a bucket sort. And then you smack them all back together. You say bucket 0 is this with this size. You then put bucket 1 next to it, then bucket 2, then bucket 3. And so the complexity of this is our operations plus the k, where k is the number of buckets, plus n, which is the size of our array again. And so this one was actually very interesting to try and code because it had a lot to do with histograms, reducing the histogram, then doing a prefix scan, an elusive prefix scan, and then scattering it into the different buckets, and then ultimately sorting those buckets and putting it back together. And so I'm going to go over the code a little bit. I'm going to break it down. And so we're going to talk about the bionic sort compare. For this, we have each thread handles one element of the array. So we can see that here. This is using the global ID. Then this if statement is a check for bounds. We're going to check to see if the thread index is out of the array. If it is, we're going to go ahead and stop. For this, we use an XOR. We compute the paired index for an XOR statement, and that is how we end up getting our paired index. And so we only use each pair once, and then we do the swap and compare. This is the if statement. Then we need to determine if it's the front part or the back part with the ascending, so it means that the up is true. And then we need to do a descending, which means the up is false. Then we assign our data, and we do our little checks to see what order they're in, and we swap depending on that order. And so the next thing I'm going to talk about is the phases in the odd even sort, because this is the really big portion of it. And so I have images from 2 different kernels here. The first one is basically doing our compare and swap. So as you can see here, we calculate the pair index with the first element of the pair. Then this is our condition statement where we go ahead and then we assign our data because it's just I and then I plus 1 because we're comparing next to each other all the times. Then we go ahead and do our swap. But this is for only one pair. Now, as you can see in our naive code, we do the pair multiple times. So we're doing it for n number of cases because that is the worst scenario. What if you have one that is all the way, what if you have your smallest number, like a 1 or a 0, all the way at your last number in your array? You're going to have to make it go all the way to the front. And by doing that, you have to do the n phases of the scenario. And so now, the last thing I'm going to talk about is the scattering the bucket sort. So each thread handles one element of the input array. Then we go ahead and check the bounds with this if statement. Then we go ahead and determine which bucket we're going to put it in, and then we're going to clamp the bucket index as well. Then we're going to get in position to do an atomic add, which gets the unique index in the bucket so there are no rare conditions or race conditions when the multiple threads write to the same bucket simultaneously. That was actually a big issue I was having, and so needed to do the atomic add of it. Then we're going to go ahead and place the elements in the output array at its computed positions. And so now I'm going to pause it and go run the code real quick to show you all the demonstration. So here we are with our main.c for all of our naive. So basically we have our verify sort, as you can see up here, and our main is like the one that we did for our labs and everything. And so that's really what it is. So now let's go to the kernel. And so first we go ahead and declare it. Then we have a CUDA call. So I had to introduce this in because I was actually getting errors and they were at every different index value. So by making this define CUDA call, I was able to determine what line they were on and in what file, and that actually helped me to solve this. So you'll see those in the code and everything. So we have our set kernel value, which helps with the padding that I talked about earlier. It has to be, the bitonic has to be a size of a power of 2, and so that's what we have to do there. And so as you can see, we have all of our code, talk about the padding that exists and that. So basically this right here is if there's no powers, it is the index or the size of the array that's getting put in is a power of 2. We don't have to go ahead and do any padding, which is why we get this global compare. We do our compare and swaps for all of them. And so if not, we have to go ahead and pad it. And it's very important to make sure you free after we're done. Then we have our odd even global, like I showed you earlier in the slides. Then we have our bucket count kernel. Then we have our scatter. And then we have our sort at the end of that. We have our sort and everything at the end. So now I'm going to go ahead and minimize this. And then go here. And we're going to nano sort.sh. And so here is what we're running. We are going to run 10,000 for 0, 1, and 2, 0 being the bitonic, 1 being our odd even, and 2 being our bucket sort. So let me just go ahead and exit out of that. And let me do MPP run of sort.sh. And so you see our bat number is 555. Going to let it run. Should be fairly quick. As you can see, it's right here. I'm going to go ahead and open that up. I'm going to open that up in Visual Studio. And as you can see, our verifications passed. We did really well. Our allocating device variable was high for our first one because that's what it usually is. And then it went down for the last two. And so we can see that our verification passed, that it is array sorted in ascending order. So now let me close out of that. And I'm going to pause the video real quick and bring up my main and kernel for my optimizations. Okay, here is our main for our second one and our optimizations. And as you can see, we have basically the exact same thing as our first one. I just created a separate main and kernel to where I could test differently. So I could have one main and kernel be for my naive, and the second one be for my optimizations. So now, going into this kernel, the bitonic sort shared was basically really hard to make work with shared memory. So I actually needed to add the shared memory, but then I needed to do a multi-parallel merge, a GPU multi-parallel merge, and so that includes the binary search, as you'll see below. So you have all this. We have our compare, and this is for our fallback if we do need it. Fallback if needed. Then we have our binary search, which partitions the array when merging, because we need that merge to merge them all together on this stage. And so we have our merge kernel, and we have our GPU multi-merge pass, and that is what gives us that. Now we have our odd-even optimization here, and so you can see we're using shared memory with the sync threads and everything, and this is making our instructions and our threads run faster because we don't have to go back to global every time. We can just use shared, and so that makes it easier and everything. And so the interesting thing about the bucket optimization was that for it, we actually needed to make a histogram. Then from our histogram, go and reduce the histogram all into one. Then we go ahead and do a prefix scan. So we'd reduce the Herschel, sum up all the histogram blocks into a global histogram. And then once we do that, we do that's for our reduced histogram. Then we scatter, and so of course we're going to use the same type of scatter with our atomic adds and everything, because that's really how you do it to get the correct positioning. And then we have our prefix sum of histogram count, and this is for the bucket offsets whenever we go ahead and put them back together and everything. Then we have our bucket sort, which is whenever we sort our buckets and whenever we put them back together. And of course, you know that we have to have our sort inside of the bucket, and that is also what is down here. And so now I'm going to go back out and I'm going to show the nano sort.sh, and that's going to pull up this. As you can see, we're going to do the exact same run and exact same test, but just with the optimizations now. So we're going to do make clean, make, just to show that it does work. I made it before for the other one. I did the make before and I ran it to make sure that it was working and everything. That's why you see the .o and .e file there as well. So now we're going to do MPP run of sort.sh, and so you see it's 556 and it's right here. So we're going to go ahead and open it. I did pick 556. You can open it and you see that it passed again. And so now that that's the demonstration done, you can see that the kernel time for all of them is a little bit larger than that of the other ones, and so that's what I'll be going into. Let me go back to my slides. And so here is the comparisons we got for them all. And so you can see we calculated the flops as well. And so what was really interesting is that for them all, the naive was basically better than any of these for the kernel time, for the kernel execution time. And it was really interesting to see that. And so the conclusion that I came to, which we can just go ahead and skip the conclusion, is that sometimes being simple produces the best results. We don't really need that optimization there, because being simple means we're doing it correct, and that means it's still really efficient, as you can see from this data. And so the first thing I can think of why that happens is whenever we used optimizations, we had so much more like kernels we had to run. And so because we had to then sync, and do our sync threads, that our instruction threads were actually running a lot faster, but we were having to do more of them, and the sync thread creates an overhead because we're having to sync, and so that overhead actually adds on to that time a little bit. And so while that does tend to add up later, and so a future optimization would be that let's see if we can combine all the kernels for everything that we're doing into one complete section, into one complete kernel, so we don't have the multiple kernels and we don't have multiple calls. We can do everything in shared memory of one thing without having to go back and read and write, go back to global, read and write, go back to global, read and write, and stop having to sync so many times. And so there are many different types of sorts. So it's best to choose the one that you seem is going to work the best for you. And so, for example, when I was working with small amounts of data, an odd-even sort may be the best sort because it can do a lot of those comparisons extremely quickly. So maybe if you're doing an array of size 10, it might be better to use an odd-even sort because it is very simple. The code was very simple to make. And so, honestly, you don't need to have that many optimizations if you're doing it for a small array. When you're doing it for a large array, that time was very, very bad. As you can see, the time got up to 18 seconds, and it almost took an hour for our optimization to run a 3 million array. So, that's not the best. And so, the best that you would want to run is a bucket sort. And that was the best that I found for the size of 3 million. There could be other ones out there, but I focused on these three. And so, but if I knew I was working with powers of 2s for my data size, I would definitely choose the Pythonic sort. And that's because it's easy to work with power of 2s with that type of sort. And so I found out that the shared memory actually takes more allocation time and then which affects the flops. So as you can see, we can go back to our comparison. Our allocation time for our shared memory was increased by about 0.3 seconds. It makes a huge deal in the big like picture, because it reduced our flops by a lot. And those flops, we need them to be very high so that we know our CPU and GPU is running properly and is doing efficient work. And so that's it for my project. Thank you for listening, and hope you have a great day.